So the point here is you can scale down your transistors, but as long as your interconnects are not scaling properly, and we'll discuss later that essentially if you scale an interconnect, its delay does not scale. The RC delay of an interconnect with scaling remains the constant. So more important as compared to the transistor delay, what has become more important is the delay coming from your interconnects. So it's so even though you might have a transistor below which is scaling, it's all the action might be killed by what's happening at the interconnect level. So there are always two ways to make any interconnect line, or in fact there are always two ways to make pattern anything, right? You can do a subtractive method, that is you deposit a film, you deposit a pattern, you pattern a photoresist and then you etch that pattern into your film. So you can then deposit this dielectric and then you can planarize it using a CMP process, and hence you achieve this structure. Another way of achieving this same structure, so this was something which was preferred for different layers in the early times of scaling in 80s and 90s, where people used to make interconnects using aluminum. This was the way it was used to make, that you deposit aluminum, you pattern it into lines and you cover it with oxide. Because again, the reason being, people know how to etch aluminum. With more and more newer materials, so now interconnects are made out of copper, because copper has a lower resistivity than aluminum, and you don't know a good etch chemistry for copper, because whatever you etch it with, it's not volatile. Similarly with all the other newer materials that people are using, even in their metal gate, they don't know how to etch them. So the other way to achieve that same pattern is you make a stencil. So you start with an oxide and you have that etched top layer, which is that blue layer. It could be a nitride, could be another dielectric, and you etch that stencil into this dielectric, and then you fill it with a material and then you polish it off. And then you essentially have that same pattern again. So to generate this pattern, you could either do it subtractively or you can do a damascene process. And these are, the reason it's called damascene is people used to, the city in Damascus where people used to make swords using this same process. So that is, so it's called a damascene process. So, right, so once you have these we finished the processing till over here, and then what we did was we patterned these plugs. So we deposit another layer of photoresist, we make these plugs, and so these are plugs which will connect to your source drain metal or your source drain silicide. So you etch these plugs into your oxide, and then you deposit it with a liner. So you deposit tinitride, and it's a CVD process or a ALD process, and it fills up this entire area. So the thing with damascene process is you need these things called liner or barrier materials. So in this case, the material you will be filling it up with tungsten. So tungsten likes to react. It's done using the CVD of tungsten is done using this precursor tungsten hexafluoride or tungsten WF4, and essentially it loves to react with oxygen and damage your oxide. So you need a liner which will prevent this precursor from reacting with your oxide. Similarly, later we will be filling things up with copper, and copper is another metal which loves to diffuse into your oxide. So you again need a barrier or a liner material. Some of the specs on this barrier or liner material are that it should first of all be a good barrier, so it should prevent materials from diffusing in. More importantly, it should have a good adhesion with your dielectric as well as the material you're trying to fill in, right? And then its resistivity should be preferably low as well, but that's a contradiction because typically materials which have low resistivity are not good barriers, because low resistivity means you have larger grains, which also means you have more grain. You have larger grain means it's easier to penetrate your grain boundaries. So the materials which are typically used for liners are amorphous materials like tinitride or tantalum nitride or materials like those, and they don't have very good resistivity. So once you have done this liner, you do a CVD of tungsten. And the thing with CVD process is that if you are doing a CVD in a trench, it goes from broad direction. So you always, if you're doing a CVD process, you're always left with the seam in between. So that's the characteristics of a CVD process. When you're trying to fill a trench with a CVD process, you many times are left with a seam, and that can be problematic sometimes. But essentially, assuming it was okay here, you polish that tungsten off and you're left with these plugs which are now connecting to your transistors below, right? So this is another picture of the A6 processor, and it is taken at this level where you can see the transistors are formed and these tungsten plugs are coming from above and connecting to these transistors. So the next and one of the final process I want to detail on is this process called dual damascene. So it's two damascene processes done at the same time. So you not only do you form, so suppose this was metal 1. So this dual damascene process will allow you to form metal 2 as well as the vias to metal 1 in this one single step process. And it's a very cool process flow. So let me describe it to you. So the way we do this is you want to minimize your RC delay. So all these dielectrics over here, these are low-K dielectrics. So low-K dielectric means either they are porous or they have carbon added into the oxide. So these are silicon SiOC. And adding carbon to it, if you deposit such a low-K film, once you're doing further processing, you want to protect it from reacting with oxygen or even reacting with resist. So you typically put a capping layer on top of this low-K film, and then what you do is you pattern a resist, and the first thing you pattern is the vias. So remember this is metal 1, so you want a set of vias that will connect it to metal 2. So for example, assume this was going in this direction, and then metal 2 would be going in this direction. You want vias that will connect your metal 1 to your metal 2. So the first thing you pattern is your vias. And you do this etch, so you make this pattern and you establish your via. The next thing you do is you fill the whole thing up with a planarization layer. So this is an organic layer, something similar to a resist, but not photosensitive. So you fill it up with this organic planarization layer, and it goes up. So it's basically a liquid solution which goes up and fills up everything, right? So you have formed this planar layer again. And then what you do is you do another set of patterning on top of this. So you you deposit another layer of photoresist, and now you want to pattern your metal 2 lines, so which are going in this direction. So this has the pattern for your metal 2 lines. And then you do a RIE etch. So you do this etch where you essentially etch this pattern into your dielectric. So now you can see, and you also etch extra into that organic planarization layer, but that doesn't matter, right? So what you're left with is you have, using 2 lithography steps but only 1 layer, you have transcribed, and using this planarization, organic planarization layer, you have transferred both of these patterns together into this 1 layer, right? So now you can remove your organic planarization layer, and what you're left with is these 2 patterns which are both now patterned into your film. So your mold is now ready. So now your template is ready. Now you can come and fill it up with a metal. So again, before filling up with the metal, so the metal we want to fill it up is with copper. So before filling it up with a copper, again you need a barrier which will prevent copper from diffusing into your oxide. So you use a tantalum nitride barrier. Some people use just a tantalum barrier. And then you also use a seed. So I'll show you the reason for that. But the process that is used for filling your lines with metal is this electrochemical deposition of copper, or also known as electroplating. So the way this copper is deposited is using electroplating. That's the same process that you use to plate your silverware or plate your jewelry. And the way it works is you have your wafer and you have your liner, and you deposit it with a thin layer of your seed material. So you deposit it with that seed material, which is shown over here. So that seed is copper, and then you dip it up in this bath, which is essentially has copper ions in it. And because you have that low resistivity seed, it will form this nice uniform electrical equipotential surface on your wafer on which your ions can now come and attach themselves, right? So that's a process of electroplating, borrowed not from the semiconductor, but borrowed by the semiconductor industry from, say, the silverware industry or the jewelry industry. But Krishna is not here today, but he did a lot of work on developing this copper electroplating process. So one of the advantage you get from doing electroplating is you get a bottoms up fill. So you have a liner, and since your ions are coming and depositing from below, you get a bottom up fill. So as compared to a CVD or a PVD process where you're depositing things from the top and it's a line of sight process, you might get a void. So that's an advantage of doing electroplating versus a PVD process. So the next step after that is to essentially CMP your material off. So there's a CMP step, and you polish your copper off. And so the question I have is so I described you one way of doing this double damascene process. There could be another way. This is shown as the other option, where you can have a hard mask. So you can make your via first. So your hard mask, you can etch the places where you want your via, and then you put your dielectric, and then you can etch together and use this hard mask to etch that via. So you can do one etch instead of doing two etch. So this is another option of making this double damascene process. So this is a final completed microprocessor, slightly older one, Power PC. But the reason I like this diagram is you can clearly see these. So these are these low-K layers, and then you can also see this capping layers, this capping oxides, and you can see all the different metal layers. And so we are almost to, this is the home run, so we are almost getting to finishing our microprocessor. So we have then the next steps are essentially continuation of this. So you did metal 1, 2, you do the same thing, metal 3, 4, metal 4, 5, 6, 7, 8, 9, right? So the only thing left is now how to connect this to the outside world, right? So we have done this, and many people don't teach this in any process classes, that you need some way to connecting this to the outside world too, right? So the way it's done is, you do your metal 9, typically that A9 or Ivy bridge that I showed you had 9 levels of metals. And then you finally, what you do is you cap it with another nitride. Nitride is another good barrier. So whenever you want to prevent things from diffusing in or out, you always cap it with a nitride, right? Then you put another resist. You open up this circular opening, and then you etch it down to your final copper layer, and then you Sorry, Wushik, it wasn't working. So you finally cap it and you put a solder liner and then you put another photoresist and then you fill copper into this photoresist and then again you dip it into a solder bath. So it's very similar to that electroplating process, but essentially you now have this region which forms up this solder. So it's like, you have formed the seed, you dip it in a solder bath again, or a solder solution, and you form this bump, and then what you do is you remove that photoresist. So what is you're left with is this micro bump. And finally what you do is you, in that chip that we showed on the very first lecture, the second lecture, is now you essentially have these bumps and you take it and connect to your PC. I mean, basically just flip the chip and mount it on top of your PCB. So this is that. So these are these small micro bumps that I just showed you how they're formed. And then you take your microprocessor, and over here you can see these micro bumps and they're connecting it to your PC.